Okay, thank you, Kai, for welcoming us and giving us an introduction to this region. I'm Laura Tomi from the Finnish Meteorological Institute, and I will be chairing this session about climate change. We have 4 presentations and time for discussion after them. And the first presentation is given by Anna Rutgersson from the Uppsala University. It's a keynote speak about climate change in the Baltic Sea Basin.
Thank you, Laura, and I also would like to thank the organizers for inviting me here to this beautiful place. So I'm Anna Rutgersson from Uppsala University in Sweden, and I'm a meteorologist, so I work with the atmosphere. I will talk about climate change in the Baltic Sea Basin, and things I will present is mainly the outcome from a book called the BAC book. So it's a big effort and a large author theme. And it is, we call it an IPCC report for the Baltic Sea Basin. So Baltic Sea Climate Change Assessment. And this book was developed within the research network called Baltic Earth, Earth System Science for the Baltic Sea region. So this is still an active network focusing interdisciplinary and international research in the Baltic Sea Basin. With some different aspects. And this is the book. It's the second assessment. So we started doing one and then we made an update. So this is the second assessment of climate change for the Baltic Sea region. So this is the basis of most of the work that I will present. I would like to start with some initial comments. The work that I will present are the changes for the past 200 years. And this is an interesting period because this is a period where we have some more reliable in situ data, and also at the end of this period there is also satellite data. So this gives us the possibility to look more reliable at changes, relatively long time changes. It's also the period where we can detect anthropogenic impacts if there are any. One should always remember in a region like ours that the internal variability of the system is very large. We have large year-to-year variation, and not everything is explained by a climate change. And in particular, if we want to look at extremes, then the long-term changes are very difficult to distinguish because they are rare by definition. So I will talk a little bit about changes in the atmosphere, in the sea, and on the land. So what we should remember here is that the climate we have is very much determined by the pressure systems that steer the cyclones. So we have NAO, the North Atlantic Oscillation, which is the strength of the low and high pressure, the Icelandic low and the Azores high. But there are also, so it's the strengths, but it's also the positioning of these systems that determine how much of the cyclonic warm and wet weather we will have. So NAO is important, as I said. So we can have a positive NAO or a negative NAO. And for a positive we get warm and wet winters, and for a negative we get cold and dry winters. And in the lower figure you can see the NAO variation since 1820. So there are periods with positive NAO and periods with negative NAO. And this, to a large extent, is determines what type of winter we have for these seasons. And it's mainly the wintertime weather that is influenced by the NAO rather than the summertime. So there is no clear impact of a climate change on the NAO, so we cannot see any indication that there is a systematic increase or decrease in positive, relative, or negative NAOs due to a warming climate. One other type of atmospheric circulation, which is very relevant now after this warm summer, is the blocking situation. And blocking situation are quasi-stationary situation and often related to extreme weather, like we have had extreme warm this summer, but also it could be other type of extreme weather. So we can have a wintertime blocking, and then we have warm conditions over southwestern Greenland. In the summertime, we relate the blocking situation to a positive phase of the NAO. And at least in Sweden, there have been a lot of discussion on the blocking situation we had this summer, whether it's related to a climate change or not. But the actual the actual system has not been shown to be controlled by a warming climate. So, to atmospheric circulation, what have been seen for the past 200 years when it comes to changes in atmospheric circulation? There has been a northward shift of the low pressure tracks, and we have seen increased frequency of anticyclonic circulation and also increased frequency of westerlies. And when it comes to the storminess, which we can reflect as the deep cyclones, it has been an increase in the number of really deep cyclones, but not an increase in the actual number of storms, but the most severe ones have been seen an increase. Here are the consecutive 10-year periods with the intensity of the storms. So, wind. Have we seen a change in the wind speed? This is reconstruction. The different curves show some different methods of reconstructing, and the bars is some uncertainty in these bars. But there are large decadal variations in the wind speed, but from the results we have been looking into, there are no clear long-term trends, so we haven't seen an increase, for example, in the wind speed. But there are periods of higher winds and lower winds, and they are often then related to periods with for example, positive NIO or high blocking activity, as is seen is this. So one need to understand the NIO when looking at changes in different features. There are some seasonal changes in the wind that has been seen. So there is an increase and a northeastward shift of the deep cyclones, and this is mainly during winter and spring. So this is the season where we see this impact the largest. There is also a slight decrease of the windiness during the fall, and these are the significant changes that the literature have shown for this period of time. So, waves. Is there a change in the surface gravity waves of the Baltic Sea Basin? So, there is no significant change in the average wave height, for example, but there are some changes seen in the spatial patterns. So, some areas with increasing significant wave height and some areas with decreasing. And this then, of course, has to do with the changes in the mean wind direction that changes the average wave field, so more southwesterly wind compared to southeasterly winds. One other factor that could be a relevance for reasons is upwelling. So along the coast we have upwelling of cold water up to the surface, and this occurs between 5 and 40% along the coast, and it's most frequent along the Swedish coast. But there has been some trends, so increasing upwelling activity along the Swedish coast and decreasing mainly along the Polish and Estonian coasts. And of course, if there is a change in the frequency of the upwelling, we also see a response in the sea surface temperature of the water along the coast. Air temperature. We see a global warming, so how is this reflected in our region? So here the blue curves are from the northern part of the Baltic Sea Basin, and the red curves are from the southern parts. And the warming for this region is larger than if we look at the global warming. This is part of the Arctic amplification. And if we look at what has happened the last decade, we have seen a continued warming. Not as much in the wintertime, more in spring. And the warming has been largest for the northern areas. And of course, if we get the warming of the atmosphere, we also get the warming of the water temperatures. And it has been significant, in particular during the last decades, in agreement then with the warming of the atmosphere. And the highest linear trend of this warming has been seen in the Bothnia Bay and the Gulfs of Finland and Riga, so the northern part of the area. A certain cooling has been seen in March. And for the lowest figure, we see that there is a strong warming, and the period shown here is from 1500, so there has been periods of warming like this also earlier. So the Baltic Sea ice. The ice cover is very much influenced by the North Atlantic Oscillation, so what type of transport system or dynamic system we have. So this is average over negative NIO and positive NIO years. So we see that the ice cover is significantly much larger on the average during a negative NIO year compared to a positive NIO year. But there is, of course, if we see a warming, there is often, it should be really linked to a decay in the ice extent. So there is a decreasing trend in the maximum ice extent of the Baltic Sea. So approximately, looking at this trend, it is about 20% per 100 years. So this is a trend that has been seen. So not only the maximum ice extent is of interest, of course. We can look at the ice thickness and the length of the ice season. And the length of the ice season has decreased. But the ice thickness is not a very clear signal seen. So for some stations there have even been an increasing trend in the ice thickness. So it's not a clear signal how this is responding to the global, or to the increase in temperature. Other parameters that might be of interest are the terrestrial cryosphere. So there is a cumulative loss, of course, then in glacier ice thickness and a decrease in glaciated area. And this has been reported for several, in general, during the recent decades. I skipped this one. So precipitation is also an important parameter. And for the precipitation is a more difficult parameter to measure and to model and to understand. It's much more variable, and it's accompanied by larger difficulties. But in general, one can say that there has been a general increase in the winter precipitation in the northern Europe. And looking at this region, the highest increase has been in Sweden and the eastern coast of the Baltic Sea. And compare further back in town, not just only the last 15 years, there are additional other type of changes with more precipitation in the southern part. But it is a difficult parameter to look into. But in general, an increase in the winter and spring precipitation. Runoff influences the Baltic Sea Basin, of course, and looking at the long-term annual river discharge, there have been no significant trends. A little bit different if we look at north or south. So in the north, the runoff is linked to temperature and the wind and the rotational circulation. In the south, the runoff is more linked to rotational and deformation circulation components. But of course, this is the annual, but as we see a warming, we get a seasonal change in the runoff. So the winter time or the springtime maximum of the runoff when the ice is melting is decreased. So we see a larger winter runoff and a smaller spring runoff because less snow is available. And there are, of course, also decadal variability and different changes for different regions. So here the blue dots are a significant positive trend, so an increase in the runoff, and the red dots show a negative trend, so a decrease in the runoff. So there are variations depending on the region we are looking at. Sea level. So sea level is a complicated feature. It's a sum of global, regional and local effects and changes due to wind, surface pressure, ocean currents, freshwater inputs and temperature. So in general, one can see that the long-term trend in the Baltic Sea is dominated by the isostatic land movement effect. So there are, of course, then falling in the northern Baltic and rising in the southern Baltic. So looking at the long-term trend and these records, and there is an absolute sea level increase, and the present rates for the Baltic Sea are large, but not similar trends have been seen also previously. There are also decadal and areal variability. So decadal sea level variability is regionally and seasonally influenced by the different large-scale forcing factors of the atmosphere. So it's correlation between sea level and NIO index, for example. So the NIO is an important factor for a lot of parameters: ice, sea level, windiness. So it's a really crucial way of describing the climate of the Baltic Sea region. Often it's not the changes in the mean parameters, the changes in the temperature or the changes in the wind that causes the largest problems for society. Often it is the extreme events that we need to change our societal systems for. So if we look at extreme events and the climate change impact, as I said earlier, it's really difficult to distinguish because they are so rare, and to have statistical signals for the climate change, we need a lot of data. But what has been seen, which I think is very interesting, is for all weather types, we see an increase in the persistence. So it means that one particular weather type stays for a longer time, and this gives a higher risk for extreme events. So from the 70s to the 90s, this persistence factor has increased by 1 to 2 days approximately. Looking at some other statistics of the extreme events, there has been an indication of the increased number of winter storms, and also the extreme temperature days, the lowest temperature days have decreased, which makes sense, of course, due to the warming. But the sum of the number of wet and dry days has increased, and the example we looked at here was from Estonia. But this is also in agreement with the persistence. We get more wet days and we get more dry days. So this is one example also from number of days with heavy precipitation, and it's also an increasing trend. So a number of days with increased precipitation. When we looked at the flooding and the runoff, we couldn't see any, this was not reflected in the occurrence of flooding, this number of days with heavy precipitation. And then looking at the more long-term trend, what has happened, there are some statistical changes. We have more tropical nights, we have more summer days, less frost days, and less ice days. But in general, it's hard to detect significant trends of extreme events. So, summarizing what we have seen from these back reports, I would like to stress again, it's difficult to look at long-term changes when we have so variable climate. So the variability is very high. But we see an increase of the persistence of weather types, which has the potential of having a large impact on extreme events. Yes, this was the same again. So if we look at the literature, within the back book and the back book concept, we thought it was important to look at the literature and see what are the changes. But it's also important to look at the literature and see where scientists disagree. What are the questions that is not the full agreement. And winter storminess is one such factor. So there are a range of studies that has indicated that there actually has been an increase in mean winds. But other studies suggest this to be a change in the density of stations over time. So there are still a lot of unanswered questions, and it's important to realize what those are. What I think, or what we thought when doing this book, are the important missing knowledge is the changes in the circulation patterns and the possibility of having changed circulation patterns due to less ice in the Arctic. And this has been hypothesized to give, for example, colder winters or other responses of the system. And this is important to understand. Other things that hasn't been investigated very much are ground frost properties. Trends in extreme events, as I said before, is difficult. But also lack of data for some parameters. And this includes, for example, clouds and radiation. Just to summarize, the parameters, some of the parameters that we were looking at, and see if we saw a long-term trend or a trend for the last decades. And as I said, it is in the last decades that we most likely can see a response of the anthropogenic greenhouse effect. So there is a change in the temperature, mainly an increase in the precipitation, and then also runoff. And these parameters that are linked to global warming, we see a negative change: ice extent, snow cover. And there are also other impacts that might change, for example, agriculture, if we look at the diurnal temperature amplitude or the length of the growing season. But in general, the variability dominates over the trend for most of the parameters. It's something to keep in mind. Yes, that was my presentation.